Okay, so let's continue then with the approximation of the Stokes problem. So we have already seen how to do mixed approximations. Mixed meaning that we use different spaces for velocity and pressure, satisfying the if-sub condition. Let's talk about, or let's try to exploit a little bit the optimization structure of the Stokes problem that we have seen in previous sessions. So this is a summary, in fact, of what we have seen before. So we have two alternatives. One is what is called strong penalization, and the other is called weak penalization. So which is the idea? The idea is that in the first case, we optimize this functional, which is the standard functional, energy functional in the space of divergence-free functions, but since we do not want to work in divergence-free functions, we penalize the functional with a large number multiplying the constraint. Okay, that's the optimization problem. The variational problem associated to this optimization is this one. So we have to find a velocity solution of this single variational equation. And the partial differential equation associated to this variational problem, if you want the boundary value problem, is this one, okay, where the pressure is minus 1 over epsilon gradient, divergence of u epsilon. On the other hand, we have what we have called weak penalization, in which what we do is to regularize, put the perturbation term in the standard Lagrangian. This is the standard Lagrangian, where pressure is a Lagrange multiplier for the incompressibility constraint, and then we regularize this Lagrangian with this term. The variational problem is this one, so we have to find u epsilon and p epsilon. Look, there is no pressure here, and here pressure is p epsilon. Solution of this system of equations. And then the partial differential equation associated to this problem has two equations. One is this one, and the other is this one, but if we replace p epsilon from this equation, we put it here, we recover exactly the first equation. So at the level of the partial differential equation, both problems are the same. So a theorem that is, again, enlightening. It's a theorem that explains a little bit the structure of the equations and the need for satisfying the if-sub condition. So suppose that u and p are the solutions to the problem with epsilon equal to 0, so the original problem, okay, the solutions of the original problem. And u epsilon and p epsilon are the solutions obtained when you put this little perturbation here. You put that term, which is p inner product with q. So then it turns out that the difference between u and u epsilon and p epsilon is of order epsilon. Okay, so this is very good. Those are good news. Those are good news because if you remember, I said that you can easily show, using a result of functional analysis, you can easily show that u epsilon converges weakly to u. You remember that comment I made? It's a sort of Weierstrass theorem, but in the infinite dimensional case. And likewise, p epsilon converges weakly to p. But that's not only what happens. It turns out that convergence is not only weak, but strong. And not only strong, but of order epsilon. So that's a lot of information. So it turns out that the difference is of order epsilon. So that's good, because we know that which order of error we are doing when we use a penalty method, okay? And the same, exactly the same happens if instead of working at the continuous level, you work with a finite element approximation that is represented here by the subscript h. So the proof is exactly the same. What I'm going to do is work in the continuous case, but the same thing, exactly the same thing, can be done at the continuous, at the finite element level. I will not detail the proof, but it's written here. So the only thing I want to stress, that's the proof. So it's simple proof. I mean, that proof, if you want to explain all the steps, is maybe a little bit more. But I want to stress that it is simple first, and the important thing is that again you need the if-sub condition. You know, that shows up everywhere. It's not only, we have seen that we need that for existence, for uniqueness, for convergence of the solution, and then now we see that we need also that proof to show that the penalized solution converges to the exact one. How does the proof go? It's not difficult. The proof, essentially what you do is you subtract this equation from the equation with epsilon equal to 0. So in the for the first equation, you get exactly that equal to 0, because both are solution of this equal to 0. And in the second equation, it's not 0, but it's something of order. When you subtract that equation with epsilon equal to 0 and with epsilon different from 0, you get a term that depends on epsilon, but you have to control it. Of course, this is positive because this is the norm of p minus p epsilon. From this, you get that. And then playing a little bit with the coercivity, and again with the second equation, as I said, this is not 0, but something of order epsilon. You can prove, you have a bound of velocities in terms of pressures, and then the IMSUP condition is what allows you to prove convergence. Well, that gives you convergence for the velocity part, and for the pressure part, you can do something similar. It's not difficult. Let's go to the discretization of the penalty method. Discretization of the penalty method. And that method is interesting. The penalty methods are interesting when the pressure space is made of discontinuous functions, those functions that we have seen in the previous session that are discontinuous. So the pressure interpolation is piecewise discontinuous. Okay, so it's a polynomial of degree 0, 1, 2, whatever, but discontinuous between elements. Yes?
For UH.
Pardon?
For UH, this convergence.
Yes.
Proof will be like that.
For UH, yes, the proof is exactly the same. You don't have to change a single word. In the we need to assume that the IMSUP condition holds, of course. What I mean is, yes, maybe I should have stressed this. Why? I say that works and we need the IMSUP condition, because sometimes people think that if you have that term that is different from 0, you don't need the IMSUP condition. This is something that you will see in many papers, not recent ones, but old papers. But that's not true, because if you don't have the IMSUP condition, you cannot guarantee that the error is of order epsilon. That's it. That's what I mean here. We have to assume that the you mean that it's not stated explicitly here? You are right. Yes, I should have said here. Yes, I am using that. I am using that the IMSUP condition holds, but I haven't stated that explicitly. Yes, you are right. I should have said that explicitly. Yeah. Yes, I am assuming that the spaces satisfy the IMSUP condition. Okay, I am assuming in the continuous case it is obvious, but in the finite element approximation, I should have said that this is true as soon as the IMSUP condition holds. Okay. Good. Let's go to the finite element approximation then. So we take one pair of finite element spaces, pressure and velocity, that satisfies the IMSUP condition with pressure discontinuous. Okay. What is the important thing? Why it is so convenient to have discontinuous pressures in this method? Let's see if I am able to explain that. If we have discontinuous pressures, what happens is that when we take the test function associated to one of the pressure nodes, the test function is different from 0 only in an element. Because imagine we have a patch of elements like that. We have a patch of elements, and we consider this element, this one. And we have, for example, a linear interpolation of pressures. Okay, for example, linear. Linear requires in 2D 3 values, 3 nodes. So if we take the test function associated to this node, in the implementation you can do it in different ways, but suppose that it takes the value 1 here, 0 here, and 0 here. Okay? This test function is 0 everywhere else. Is 0. It's only different from 0 in this element. It's discontinuous. Okay? So it's like a plane that takes the value 1 here, value 0 here, and it's 0 everywhere else. That's the test function associated to that node, right? Okay, that function is different from 0 outside element K. That only happens if you have discontinuous pressures, because if we had continuous pressure, for example, if we take that node, the test function associated to this node is different from 0 on all the elements that share that node. You see? So But if we have a test function that is different from 0 only in an element, integrals will extend only over the element. So that's what we have, that when the test function is the shape function of a certain pressure node, it's different from 0 in the element where node A belongs, and it's 0 outside K. So here we only have the test function different from 0 in an element. And that is very important because when we have all the integrals that extend over all the computational domain, restrict now to the element. Restrict now to the element. So what is the weak form of the continuity equation? Which is the weak form of this equation? Which is the weak form? The weak form is this one we discretize. We have sum for all nodes of the pressure shape function times the pressure nodal values. That is the pressure, you know. When we sum for all nodal values, this is the pressure interpolation. And then multiplied by the pressure test function, plus the divergence of the velocity. The divergence of the velocity is sum for all nodes C, nodal value of C, nodal value at node C of velocity multiplied by the derivative with respect to the component I of the shape function of the velocity, and summing for I. Okay, this is the divergence of the velocity, and that again multiplied by the test function QH. Do you all see that this is the expression that you get once you discretize using finite elements this equation? Okay, look at this equation, and look at this expression. Do you all see that that's what we get? Good. Perfect. So now what is the expression, what is the structure of this equation? The structure of this equation is the following. We have epsilon, then we have a matrix multiplying the pressure nodal values, and another matrix multiplying the velocity nodal values. But what is the important point? The important point is that this integral extends only over element K, not over all the computational domain, but only over element K. And therefore, this matrix needs to be defined only element-wise. And so, for example, in the case of this linear interpolation for pressures, this is a matrix of which size? What is the size of this matrix in that case? Within each element, how many pressure nodes do you have? 3. This is a 3 times 3 matrix. You see? Within each element, there are only 3 pressure nodes. So this is a 3 times 3 matrix. You see? And that is bigger, of course, since the velocity interpolation is continuous. This is a matrix that is 3 pressure test functions, but, I mean, as many degrees of freedom for the velocity as needed. Okay? But the important point is that this matrix is 3 times 3. And, you know, we all dare to invert the matrices of dimension 3 times 3. So we can explicitly eliminate or compute, if you want, the values of the pressure inside element K from this expression. Okay? We are able to do that. So we do this because we are able to invert, I mean, it is computationally feasible to invert a matrix of size 3 times 3, or 4 times 4, or 7 times 7 maybe. Not of 1,000 times 1,000, or 10 billion times 10 billion, but of 3 times 3 it is possible. So now, if we go back to the momentum equation, we can write the momentum equation as the viscous term plus the sum for all the elements, because the integral is additive. So the integral can be written as the sum for all the elements of the local integrals. And then we have the local values, the matrix D restricted to element K times the degrees of freedom of element K. That we can always do. But now the point is that the degrees of freedom of element K have been explicitly obtained in terms of the velocity degrees of freedom. So we just replace this expression here, and we get that. So what we get is K multiplying the degrees of freedom of velocity, and here we have epsilon minus 1, and then what is that? What is the local calculation of these element matrices and then summing for all elements? This is the so-called assembly, okay, the assembly process in finite elements. Okay, you compute matrices locally, and then you expand them, you sum for all elements, and you expand them to the global matrix. You know that process? Okay, that's the so-called assembly process. Sometimes this is not a common symbol. Many people use that, but not everybody. This is the so-called assembly operator. So that is interesting, because what do we have to do here? You see, we have to compute local matrices, one inverse, but perfectly affordable, local matrix, and we have to assemble them. And likewise, we have the matrix K that comes from the viscous term. And what is the advantage of this? The advantage of this is that we have obtained the problem posed in terms of the velocity alone. So we have eliminated the pressure. Okay, we have eliminated the pressure, and that's very good. No pressure there. Okay, so some comments. First is that matrix is symmetric and positive definite. So when you don't have that epsilon, you need to pivot. You need pivoting. Why? Because in the original system, in the original algebraic system, I don't have it here. In the original algebraic system, where is it? Here. In the original algebraic system, we have a 0 in the p position. So the matrix is K minus D transpose D 0, okay? And if you have a 0, when you solve that system using a direct method, then you need pivoting to avoid dividing by 0. In fact, one of the main problems at the computational level of these mixed methods is the appearance of these zeros. But I am talking about stability and convergence and good properties of the method. But when you put that on the computer, it is also important to obtain a method that is of easy implementation. And when you have zeros, it's not that easy to implement. Why? Because if you use a direct method to solve that system, you need pivoting. And you could say, for a large number of degrees of freedom, we will never use a direct method. That's true. But you know that if you use an iterative method, you always need to precondition that method, okay? You always need to precondition. And if you precondition, you need to solve, let's say, at the end, you always need to solve small systems of a certain bandwidth. I mean, the preconditioning matrix is constructed from the original matrix and with a certain bandwidth, for example, in complete LU, whatever. I don't know how much you know about that, but about solving linear systems, but you always have to precondition. So at the end, if you have zeros in the diagonal, you also have to, you need pivoting always, okay? So it's very good if you don't have a zero in the diagonal. That's the conclusion. It's very convenient. It's very convenient if you don't have a zero in the diagonal. Okay. So here you don't have a 0 in the diagonal. This matrix is symmetric and positive, positive definite. But the bad news, the very bad news, is that the condition number of that matrix is of the order of epsilon to the minus 1. So if epsilon is very small, that number is very large, and iterative solvers are unfeasible, because you know that the rate of convergence of iterative solvers, algebraic iterative solvers, depends linearly on K, on G, the condition number, okay? You know that the condition number is the ratio between the largest and the smallest eigenvalue of the matrix. Okay. Let's go about the strong penalization. The strong penalization is not recommendable at all. What we have to solve is this problem. When we do finite elements, we construct only the velocity space. There is no pressure. Why? Why there is no pressure? Because even in the finite element case, the pressure associated to that problem is minus 1 over epsilon divergence of u epsilon, even in this case. So in a sense, we don't have the freedom to choose the pressure space. The pressure space is given. The pressure space, pressures are divergence of functions in the velocity space. So it's given. We don't have that freedom. And if we don't have the freedom to choose the pressure space, what do you think might happen? So we don't have any freedom. Once we decide which is the velocity space, the pressure space is given. So what might be the problem of this? I'm not saying that it will always be a problem. I say that it might be a problem. If the pressure space is given, what happens with the if condition? We don't know. The answer is that we don't know. We have no choice, no freedom to choose the pressure space. And therefore, once the velocity space is constructed, the pressure space is given. And it might well happen that that pair is not stable. And that happens, in fact. So it's not that it might happen, but that happens, okay? Okay, so this method is, in a sense, is very similar to the previous one, but with the pressure space given. Not chosen, but given, okay? This is the matrix form. That's the matrix form. So that matrix is called volumetric matrix, volumetric stiffness matrix in the literature. That's the expression. So we have a matrix that comes from here. And that, displays a phenomenon in general, which is called locking. Okay? This is a terminology that you will see also in other problems, but the origin is the Stokes problem. In fact, not for fluids, but for solids. That was well known for solids, both elasticity and plates. Okay, and locking. Locking is a terrifying word in structural mechanics. Locking. What does it mean, locking? It means that if that matrix happens to be non-singular for any reason, suppose that of course, the global matrix has to be non-singular because you want to invert the problem. But if this one is non-singular, what will happen? If this one is non-singular, it will happen that when epsilon goes to 0, that will dominate over that one. If this one is non-singular, that will definitely dominate. If this dominates, the solution is going to be u equal to 0 because this dominates, so that one doesn't count. 1 over epsilon kb u equal to f, but then you move epsilon to the right, and you get that when epsilon goes to 0, the solution goes to 0. That is called locking. Okay. And here there is a, let's say, under integration. When I was looking at that, I was hesitating about whether I should put that or not. But since it's history, and that's culture is also important, I have included it. It's more a historical remark rather than something interesting. That matrix is not singular. Okay. So the idea that some people had was try to make it singular, to approximate it by a singular matrix. And the idea and the way to do that is using what is called under integration. So use a low order quadrature rule, integration rule, that yields a rank deficient matrix. So that sounds strange, you know. I mean, you have to, then we'll see the justification. But we have to integrate numerically, using numerical integration, you know, that's the expression of the matrix. But we have to use a low order integration rule so that that matrix is not exact, is not exactly computed. And thanks to the fact that it is not exactly computed, it's not invertible, it's singular. And thanks to the fact that it is singular, that problem is not dominated by this term. It's sort of strange, isn't it? But it's how it is. That was called under integration, and that's the. I mean, it's old, but not that old. I mean, it's an old method, but not that old. So it was originally introduced by Sienkiewicz, Taylor, and Tu early in '73. Then in plates, Fried, and then in elasticity, and formalized by Tinsley-Owen. Okay. Well, the final method was called reduced integration penalty method. And the idea is to find velocity such that this equation holds. But you see there is a star here. And that star means that this is not computed exactly, but using a low order quadrature with a certain number of integration points and int. Okay, that's called under integration, RIP method. And it turns out that well, there's a result, a curious result. It's not very useful, but it's curious. It turns out that if you define the space of piecewise polynomials that are an int, and int is the number of integration points, unisolvent. What does it mean? It means that those are the polynomials uniquely defined by those integration points. For example, if you have a single integration point here, what is the space of one unisolvent polynomials? Piecewise constants. I mean, if you have only one point, you can only define a polynomial of degree 0. If you have 3 points, you could define a linear polynomial. But if you have 2, again, it's only one unisolvent because you can only define uniquely a polynomial of degree 0, a constant. I'm talking in 2D. Do you understand what I mean? Okay. So that is what is unisolvent. So if you define QH as the space of polynomials that are in unisolvent, so uniquely defined by that number of points, if you can show that integration rule star is exact for functions in that space, and also for functions in that space divergence of velocities, then the RIP method is exactly equivalent to the width penalization. Exactly equivalent to the width penalization. And that's the proof. Okay, it's not difficult. You have to use unisolvency and not much more. So that is the idea. And that was proved, that was exploited for the Q1 element, for the linear element. For the linear element, it turns out that if you consider one method, which is the weak penalty method with Q1 P0, so that is bilinear velocities and piecewise constant pressures. That's method 1. And then you consider method 2, which is the RIP method with only one point integration, piecewise constants. Then it turns out that you can show analytically that that method A, is exactly equivalent to the RIP method. Exactly equivalent. And these two properties happen to be true, so that's exactly equivalent. So what is the problem? So in that case, and that was very much exploited, you know. I mean, Q1 bilinear velocities with reduced integration of piecewise constants was with only one point integration. That was exploited a lot in the 80s. No, not now. Now it's a little bit. But what is the problem? The problem is that the element that you recover is the Q1 P0. Do you remember what I said this morning about the Q1 P0? Who does remember that? What did I say about this element? Is it stable or it is not? No? Exactly. It's a very curious element, okay? It's a curious element. If the mesh is structured, it's not stable. But if the mesh is, you know, non-structured, it is. Maybe I should have said that because, again, I have said now a minute ago that culture is important. and this element has also some historical, let's say, importance, you know. It turns out that if you solve a problem in a mesh like that, very structured, why is it not stable? What is it not stable? It is not stable for a very interesting reason. It is not stable because there is a pressure array which is 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, and so on. If you take that array, it turns out that the gradient of that array is 0. The gradient, the minus the divergence of this array happens to be 0. Now, if this array has a discrete gradient 0, and of course it's not 0, neither 0, not a constant because it's 1 minus 1. What happens with this problem? KU minus D transpose P, let's call it P0. P0 equals to F, and divergence of U equal to 0. What happens with this problem? Of course, if you have a solution P, if you add any multiple of P0, that's going to be a solution again, because D transpose of P0 is 0. You see? So if you have a solution, if you add that term, that's going to be a solution again. And lambda can be anything you wish. So that element displays what is called a checkboard mode for obvious reasons, okay? Because you have that, it's called a checkboard mode. Okay, so it's not a very good element. It's not a very good element, but in some situations it works. By the way, that mode can be filtered. That is also true. But anyway. Okay, so we are done. We know the structure. We know how to approximate with and without penalization. So first we saw how to approximate without penalization. Then we have seen that it is possible to optimize the penalized problem, to approximate the penalized problem. But nevertheless, the main reason why, apart from the fact that it is interesting in some problems, I have I wanted to emphasize that even if you use a penalty method, you need to satisfy the IMSUP condition. Okay. Now we will go very fast. Very fast. Why? Because now we have to. We don't want to satisfy the IMSUP condition, and we want to use stabilized formulations. Why will we go so fast? Because most of this section, not all, but most of this section is what I already explained before for convection diffusion reaction systems in general. Now we will apply it to the Stokes problem, but I will explain that for convection diffusion reaction systems, okay? So that's what we will do. That will be very simple, and I will go very fast through that, only emphasizing what is new and what I haven't said. Now with the perspective of mixed formulations introduced before. Okay. Which is the motivation of using stabilized finite element methods? I mentioned that yesterday. Here it is written. There are, in general, two big families of problems that require stabilization. One is singular perturbation problems, and the other is non-definite bilinear forms with non-trivial IMSUP condition. Of course, in some cases, in some problems, the IMSUP condition is trivial to satisfy. So you have a mixed problem, so you have different variables, but the IMSUP condition is so natural that you don't have to worry. Okay? But for the Stokes problem, the IMSUP condition, you do have to worry. It's not trivial. For the Stokes problem, the difficulty is either because we don't want to satisfy the IMSUP condition. Why don't we want to satisfy the IMSUP condition? For example, because we want to use equal velocity pressure interpolation. This is what is most convenient from the computational point of view. Okay, to use the same interpolation for the velocity and the pressure. Everywhere you have seen before that I was playing with the velocity shape functions and the pressure shape functions. So I put this subscript u for the velocity and p for the pressure everywhere. Okay, but it would be very nice if in our code we just can use a single set of shape functions and shape functions derivatives and so on. So equal interpolation. But sometimes it is also interesting not to use equal interpolation, but to stabilize, to make useful convenient elements such as Q1P0 and P1P0. So for example, Q1P0, that's the element I was mentioning, for regular meshes is not stable. So we may insist in using that, I mean, for any reason. Okay, maybe because you like discontinuous pressures, which is a piecewise constant. That is, and for example, one element that is very nice but absolutely unstable, is the P1P0. So P1P0 would be linear velocities, and constant, piecewise constant pressures. This is absolutely discontinuous. In general, if you, of course, I mean, let me also spend a minute on that. In general, if you want to satisfy the IMSUP condition, let me write the IMSUP condition in this in the IMSUP way. The infimum for all Q's, or QH, of the sup for all VH, understanding that for all QH in the pressure space and for all VH in the pressure in the velocity space different from zero, so on, of QH divergence of VH normalized VH greater or equal a positive constant. Of course, when is it going to be easier to satisfy this condition? When the velocity space is larger or smaller? Large, of course. I mean, the larger the velocity space, the easier this condition to hold. Or vice versa. The smaller the pressure space, the easier this condition to hold. Okay? So, in general, if you have a method that if you don't really know if it is stable, if you reduce the number of pressure unknowns, you will improve stability, and vice versa. If you increase the number of velocity unknowns, you will improve stability. What happens? Imagine you have a square and you discretize it in triangles. It's the same, or a similar count to what I did this morning. So imagine you discretize it in triangles. So or in quads. You know that if we discretize it in quads, we would use elements of this type using P1, P0. So P1, P0 would be this. Okay? And that element is, you know, in the border. For regular meshes, it doesn't work. In other cases, it does work. In fact, it gives very good results when it works. I like that element very much. But if you discretize it using triangles, if we look at one of these cells, what happens? It happens that you have the same number of velocity unknowns, but you double the number of pressure unknowns if you use the P1, P0. So in the P1, P0, the ratio velocity unknowns over pressure unknowns is 1/2 of the ratio of velocity unknowns over pressure unknowns than in the P1, P0. Okay, if that element was, you know, there in the border, this is definitely on the bad side of the border. Okay, do you understand what I mean? So the element, the P1, P0 is very unstable, very unstable. Okay. So there are these two reasons. So I mean, you don't want to satisfy the IMSUP condition either because you want to use, for example, equal velocity pressure interpolation, or you want to use convenient elements such as Q1 P0 or P1 P0. No. Other examples that need stabilization, well, convection diffusion, we have seen that. Reaction diffusion, that's what we have seen. Plate problems, Darcy's problems, waves, methods based on, I don't know, deflection, momentum expressions, and there are many, flux, velocity. There are many problems that require that. Of course, the stream function vorticity formulation. There are many examples that require that. For the stream function vorticity formulation, for those of you that work in fluid mechanics, it's another way to write the flow equations. In finite differences, it is almost trivial to find the method to obtain an infinite stable formulation. In finite elements, you have to work a little more. It's not that easy. It's non-trivial at all. Anyway, there are many examples that need stabilization because of the IMSUP condition. Now we will do exactly the same that we did yesterday, so that's why I said we will go fast here. So we'll write the Stokes problem as a system of equations, the momentum equation, the incompressibility equation. Now we identify the first order terms, gradient of pressure, divergence of velocity, as, let's say, convective terms, quote unquote, okay? Convective terms, if we write them this way. Now we apply an SUPG strategy. As you see, those are the same slides as yesterday, now in the context, in the chapter about the Stokes. We apply the SUPG strategy. We take a perturbation of the test function given by these, okay? And we choose tau to be diagonal and with this expression in 2D. So one component for the first equation, for the momentum equation, and another component for the continuity equation. So we're applying the SUPG strategy. We have to add these two terms in blue to the Galerkin terms. So I'm recalling what I explained yesterday. We have to add these two terms in blue. Okay, so it's again the convective operator applied to the residual of the finite element solution. So we have the first component of that operator applied to the first equation, and the second component of that operator applied to the second equation. That has the structure which is written here: residual multiplied by a certain perturbation of the test function, where P, in that case, is only part of the Stokes operator. So the GLS method, the idea of the GLS method is to, instead of only putting part of the Stokes operator, to put everything applied to the test function. So we have, for component 1, L1 of VQ, for component 2, L2 of VQ, and the component 1 has not only the pressure gradient, but also the viscous term. That's the difference. That's the only difference with respect to the SUPG. And that leads to the GLS method. The reason for the name, I explained that yesterday, and the structure of the discrete system, I also explained that yesterday. So that's exactly the same as was said yesterday. Okay. So, and that's the convergence theorem. Again, the convergence that I introduced yesterday. No problem with that, the same remarks. Well, yes, maybe that remark I didn't make. If you if you have a tau 2 which is different from 0, you can prove stability and convergence in a norm that includes the divergence of the velocity as well. Well, that I didn't explain because I wanted to leave it for today. If you remember, I said I will explain that when talking about the Stokes problem. Now we know what is the Q1P0 element, for example, which does not satisfy the IMSUB condition. And there are other elements that don't satisfy that condition. For example, the P1P0, or for example, P2P1. P2P1 does not satisfy it. One has to introduce a bubble. And suppose that you want to make it work. You want to make it work for any reason. Sometimes it's interesting. This element, for example, this particular element, which is very strange, does not work because, as I have explained, there are spurious pressure modes, which spurious meaning that they are different from 0, but the gradient, the discrete gradient, is 0. And also another problem is that in general you can only prove that the IMSUB constant is of order h. So the IMSUB, well, sometimes I call it beta, sometimes I call it kb. The IMSUB constant is of order h. This is not true. This is what you can prove because the only thing you can prove is that because in regular meshes that's what you have. In non-regular meshes, in fact, it's bounded from below by a constant independent of h. At least that's what it said here. Okay, at least for regular meshes. In general, it is believed but not proved that that element has a IMSUB constant independent of h. Okay. Well, how could we stabilize that? How could we stabilize that? Well, suppose that we have a partition of omega into patches of 2 times 2 meshes. Oops. Suppose that we have a partition of omega which is not general but is such that it allows you to construct, so you have a partition of the domain, whatever, partition of the domain into patches of 2 times 2 Q1P0 elements, okay? So the mesh is such that you can, let's say this is a macro mesh that is composed of 2 times 2 Q1P0 elements, okay? And suppose that gamma, what is called here gamma P, is the collection of interior edges of patch number P. And this bracket, double bracket, is the jump operator. What does it mean? So it means that we consider those edges. We consider those edges, okay? And we define the jump operator. What is the jump operator? The jump operator is nothing but the jump of a function f is nothing but the function f on one side minus the function f on the other. So that we can write it this way, the function f from one side minus the other. In principle, you have to choose what is plus or what is minus, okay? Obviously. So, for example, if you have two elements, you have to decide that this is plus and this is minus, for example. However, in fact, in discontinuous Galerkin methods, it is very important to define well these jumps. But here, in what we need, it's not important because we will always have jumps multiplied by jumps, always. So it doesn't matter whether you decide that this is plus and this is minus or the other way around, because at the end, the product of a jump times a jump will have the same sign, either if you choose one or the other, okay? In principle, you could have a change in sign, but since we will always have products of jumps, that doesn't matter. Okay. So that element, there was a paper by Sylvester and Ketchker who showed that that element, the Q1P0, can be stabilized, can be made stable, if to the Galerkin continuity equation, that is the Galerkin continuity equation, you add the sum for all the patches of the integral of the jump of the pressure test function times the jump of the pressure multiplied by a parameter alpha multiplied by h, the element size. That method happens to be stable. This is a paper, old paper, in the beginning of the 90s, I would say, by Sylvester and Ketchker. Well, that can be generalized. That can be generalized. That idea leads to that general convergence result. Consider the Galerkin least squares method. with associated by linear form, and then we add, to stabilize elements that have discontinuous pressures, we add the sum for all the edges. If you want to be general, you have to add the sum for all the edges, not only the elements in a patch like here, but the sum for all the edges, all interior edges, of the jump of the pressure test function multiplied by the jump of the pressure, okay, where the sum extends over all the internal edges into the orifices in 3D. Pardon me?
This term in the second.
And we add that to the second equation, exactly, exactly. Enlarge with the term. Yes, I didn't say in the second equation, because since it involves only the pressure test function, if you write the problem as a single variational equation, it will go to the second equation once you take the pressure test function equal to 0 to obtain the first equation, and it will contribute to the continuity equation when you take the velocity test function equal to 0, you know. I mean, you have the method, you have a single linear form, so it's always good to look at the problem as a single equation, okay? So you have the problem with a single equation, and to that equation you add this term. That's it. And then, of course, it will go to the second equation, as you say. Okay, so it turns out that then define that mesh-dependent norm, which is defined here, the triple norm, which has, again, I'm missing the gradient here everywhere. That's the gradient of the velocity squared plus the norm that we had for the Galerkin method, the Galerkin least squares method, plus that term, which is the sum for all the edges of E alpha h times the jump square. Then, if the constant c tau is small enough, that c tau is defined here. Okay, so tau 1 has to be of this form. If the constant tau is small enough, maybe I will show you what doesn't mean small enough. Maybe, let's see. What doesn't mean small enough? Then the method is stable and optimally convergent in this norm. If one of the conditions is verified, by the way. Well, but this is a general convergence result, so you have to add that. So if one of the following conditions is verified, then the method is stable and convergent. Which are these conditions? First, pressures are continuous. If pressures are continuous, of course, this term does not appear, and we are back to the result that we already know, okay? So if pressures are continuous, nothing. If this term is activated, if we activate this term, alpha is positive, then the method is stable and optimally convergent. Or, that is somehow surprising, even if that term is equal to 0, the method happens to be stable if the interpolation order is higher than the space dimension. So if you have velocity interpolations of high order, then the method is convergent, even if this is equal to 0. The proof is not difficult, but maybe, as I said, I will explain a little bit how this analysis goes, and in particular, the only thing that is a little bit that I would like to explain, in fact, rather than the technicalities, is that the conditions on that constant, because we haven't paid much attention to this expression, and in fact, it's very important. Okay, clearly, it has to behave as h squared over viscosity. This is a simple dimensional argument, scaling argument, if you want. But we haven't talked much about that constant, and maybe I should. Maybe I will mention it now. Maybe I will mention it now. Let's break. Let's break. No, I am finishing, right? No, I have half an hour yet. Yes, I have half an hour. Let's break 10 minutes, not less than 10 minutes. Let's break less than 10 minutes. We will see later. I can break now. I can make a break now, because we already know the next method, which is going to be with the adjoint. Okay, because it's easier to explain that with the adjoint. Look, consider the following approximation of the Stokes problem: nu gradient of UH, gradient of BH, minus PH divergence of BH, plus QH divergence of UH. So this is those are the Galerkin terms, plus the sum for all the elements of tau, and then the integral over each element of, I put a plus. It's I would put a minus. The same thing happens, but it's better to put a plus. Gradient of QH, comma, minus nu Laplacian of UH, plus gradient of PH, minus f over element k equal to 0. Okay? This is the GLS method. Not exactly the GLS method. So this is this method. This method with a change. Well, if you want here, this method. And the only thing I've done is to change. Well, I have taken tau 2 equal to 0. It's not important, and I have changed the sign of that term. That is what happens with when we use minus the adjoint. Okay. And the only thing I want to stress is something to which we haven't paid much attention, which is that constant, that algorithmic constant. And I want to make two remarks about that. One is the limitation of that constant, and the other is the implication of that constant. So what is the limitation of that constant? Let's try to prove a stability here. Let's try to prove a stability. How can we prove a stability? We take the test function, the most naive idea. It's not the only one, but it's the one that is used most of the times. And the most naive is to take the test function equal to the unknown. Okay, we take the test function equal to the unknown. What happens? What we will get is nu gradient of UH squared. This term will cancel with this one, plus sum for all the elements of tau k times what? Times what? Let's forget that. Well, by the way, there is missing the right-hand side here, okay? I am only considering the bilinear form of the problem. What do we have? Look, we have gradient of p, and here we have Laplacian of u minus Laplacian of u. So it has the structure a plus b multiplied by minus a plus b. You see? A plus b times minus a plus b. And of course, this is b squared minus a squared. Okay? So that's going to be gradient of pH squared minus nu squared Laplacian of UH squared over each element. That is over each element, okay? Over each element. Okay. So now we have said that tau has to behave as a constant times h squared over viscosity. Okay? Well, that's only the left-hand side, because I am only concerned in the bilinear form. You know, what is on the right-hand side doesn't matter if the method is stable, okay? So I'm not saying that this is equal to this. I'm just considering the let's say the right-hand side, the left-hand side is equal to this. And then if we take this, we have this is equal to nu gradient of UH squared plus h squared over nu times the constant gradient of pH squared minus sum for all the elements of that viscosity cancels with that square, so we have c tau h squared viscosity, and then Laplacian of UH over element k, right? So there is a property of finite element interpolations which is very useful in the analysis, well, I mean absolutely necessary in the analysis, which is called the inverse estimate. What is an inverse estimate? It happens that for any finite element in space, in general, you know, derivatives of order whatever n can be bounded in terms of derivative of order n minus 1. So in particular, the Laplacian of UH can be bounded in terms of the gradient of UH. Of course, there is a price to pay here. Which is the price to pay? Why there is a price to pay? Because if not, that would be impossible. Because not if we have a function that has the gradient bounded, automatically the Laplacian would be bounded. So we have a function of regularity p. Automatically we would have regularity p plus 1. If we have p plus 1, p plus 2, and so on and so forth. So that's not possible. What is the price to pay? The price to pay is a power of h loose. Okay, so there is a 1 over h here. And you see, units are very important. So here we have one more derivative than here. So here we have 1 over length more here than there, and that scale is precisely the element size. Okay, and the constant depends on the constant that appears here is the inverse constant, the so-called inverse constant, and that constant depends on the shape of the element and the order of the interpolation. But it's given, it doesn't depend on anything else. Once you define the shape of the element and once you define the order of interpolation, it's given. Okay. Therefore, if I use this property, let me erase that. That is greater or equal. That is greater or equal, because this is smaller or equal, so I have a minus. That's going to be greater or equal the following: nu gradient of UH squared plus the sum of C tau H squared over viscosity gradient of pH squared minus C tau times H squared will cancel with the inverse estimate. So we will have the inverse constant. The way I've written that is C imb squared, okay, because we have a square here. We have the viscosity, and then we would have the gradient of UH squared over element K. Sum for all the elements, okay? So for all. See? I have used the inverse estimate. That's the only thing I've done. Now, the point is that this term can be grouped with this one. And therefore, we have that this is equal to viscosity gradient of UH squared times 1 minus C tau C imb squared plus the pressure term plus the sum over elements of C tau H squared over viscosity gradient of pH. So now, when we see that, we clearly see what does it mean. What does it mean? C tau sufficiently small. What does it mean? C tau has to be smaller. So we want to make that positive. So C tau has to be smaller than the inverse of C of the constant of the inverse inequality squared. That's the condition. Okay. So this has to be greater than 0, and that poses a condition on tau, on C tau. Is it clear? That's one thing. And the other thing, so that's tau has to be sufficiently small, but not too small, because if it's too small, then we will not have enough control on the pressure. You see? Okay, so is it very important to choose the good tau? Yes and not. So first, it cannot be very large. It cannot be very large, because otherwise you will violate that condition. And in practice, that happens. If you take the constant too large, you will get into trouble. You will get good results. So one point is, first, C tau has to be small enough. That is the point. In small enough, that's the first point. And the other is, once C tau belongs to a certain range, because it cannot be too large. But it cannot be too small, because otherwise we don't have control on the pressure. So if you choose tau in a range in which the method works, what is the effect of tau? Or C tau, excuse me, C tau, the constant. Well, the effect is the following. Imagine you plot the error, the convergence curve of the method. So you plot the error, for example, in velocities, for example, u minus UH, in any norm, for example, in L2 or in H1, you plot the error against the mesh size. Usually, you do it in logarithm of the error against the logarithm of H with minus. Okay. If you remember, the error behaves as the H to the power of the polynomial order in H1. Okay. That's the way the error behaves, roughly. So what you will get when you take the logarithm is something like that with a slope precisely p, the polynomial order. That's what you will get. Okay, if you have the good range of constants, you will always get that. However, for a given mesh size, you can get better or worse solutions depending if you choose the constant, the appropriate constant or not. What does that mean? That maybe for a given H you get a worse or a better solution if you change the constant. But what we obtain when we do numerical analysis is always the convergence rate. And the convergence rate is going to be the same. It's going to be the same, okay? So changing the constant, of course, changes the error. Of course it does. But it doesn't change the convergence rate. So some people argue, particularly from the engineering community, the solution depends on the constant. Of course it does. Of course the solution depends on the constant. But the solution depends also on the shape of the element. So when you have a mesh, you say, okay, triangles have a certain rate of convergence. But you have one rate of convergence if the triangle is like this, and another rate of convergence if the triangle is like that. You understand? So, I mean, you cannot complain about that. That's something that happens. I mean, once you have a certain mesh, a certain geometry, a certain constant, then you will have a rate of convergence with an error that may be bigger or smaller depending on how the constant is or how the shape of the element is. You understand? So all what we are doing is we are giving convergence estimates in terms of rates, never absolute values. That is something that you cannot do. That is the objective of a posteriori error estimation. Once you have a solution, you want to compute exactly the error, the error that you have done. That's what you want to do for a given age. But that's not what we are doing now. Okay. So about your remark. So how did you pose the question originally? You were saying what?
That jump term.
Yes, you were asking about the jump term, but your question was precise, and I said I would go back to it later. Which was your question exactly? Which what?
That jump term.
The jump term?
Yes.
What happens with it?
Means it will stabilize the solution or what it will.
Yes, yes, I remember now. Why is it essential? Why is it essential? Imagine you have the method that I have written right a minute ago. Is Galerkin plus sum for all the elements of tau k times minus or plus new Laplacian of BH plus gradient of QH times minus new Laplacian of UH plus gradient of PH minus F. Okay? Suppose that's the method. And now imagine that you want to use the P1, P0 element. That's one element that I said is convenient because pressures are piecewise constant, velocities are linear. What is the value of this term? The gradient will be 0. And what about the Laplacian? What about the Laplacian? P1 means linear velocities. 0. So this is 0. Okay, and the method is completely unstable. So that term is definitely not enough. So you have to add, that's what that theorem says, you have to add something that is the sum for all the edges of the partition of a certain parameter that behaves as alpha constant times h times the integral over the edge of the jump of the pressure times the jump of the pressure, of the pressure test function times the jump of the pressure. Okay. In fact, we have a method that is slightly different to that one. Our method is different, but I try not to explain our methods. Okay. Well, that's it. That's the general convergence result. I didn't explain that in detail yesterday because we didn't know what the Q1 P0 element is, for example. Okay. So now we also analyzed the GLS with P1 elements, and we saw that the GLS with P1 elements is equivalent to the Galerkin method with that element, the so-called mini element that we have seen today. Okay, we saw the explanation yesterday, and that after condensation the bubbles, and that leads. This is exactly the same slides as yesterday, and that leads to the introduction of bubbles. as stabilization techniques, okay, to the introduction of bubbles as a stabilization method. Okay, but then we said, okay, let's forget about SUPG, let's forget about GLS, let's forget about bubble functions, and let's design a general framework. That's exactly what we did yesterday, okay? And the general framework is what was explained yesterday in the same slides and that are repeated here. The general framework is, we have any variational problem, we split the solution into the finite element component and the complement. Here is correct. You see, I haven't put subscript here, so this is correct. So we split the solution. Then we do the same as yesterday. We integrate by parts these terms. Do you remember why do we want to integrate by parts this term? Do you remember the argument why we want to have isolated U tilde? Because, yeah, no, only in the interior, yes, but up to this point, when I say that it's defined only in the interior, it's because I take that equal to 0, but that was later, First we said, if we were able to obtain U tilde from this equation, if we could obtain U tilde from this equation, we could go directly here, insert U tilde, and that's it. But we don't do that. We integrate by parts. Why? Why do we want to have U tilde alone? Do you remember the argument? Exactly. We cannot expect to have a good approximation to the derivative. We can expect to have only a good approximation to the mean value, to the effect of the subscale. Remember that at the end, remember what we saw yesterday. At the end, I put one example in 1D. So the real subscale, even if it is a bubble, even if it is 0 here, the real subscale is like that, you know, whatever. Even if it is 0 on the boundary, even if this assumption is true, which is not necessarily does not necessarily hold. At the end, we approximate the subscale by a constant or a linear function. Do you remember this? Hoping that the effect of this subscale is the correct one on the finite element solution. But of course, if we approximate the subscale by this, we cannot expect to have the good derivatives. This is obvious, okay? This is obvious. So that's why we integrate by parts here. We integrate by parts and we get the subscale isolated. And then we obtain the subscale from this equation and we insert it here. That's exactly what we said. The same slide. So we have to solve the problem for the subscales. We have a lot of options. We will choose these two. We have to solve this problem. And once we solve the arguments, Green's function, the approximate Green's function, that's what we said, and the bottom line, which is this one, okay? That is the method, okay? This is the method, adding this term. Then we could, instead of approximating the Green's function, we could approximate using bubbles. The bubbles introduce a certain approximation of the Green's function. And we could even use what are called residual free bubbles that have some interest. But we all know that. We know that from what was said yesterday. So at the end, in the case of the Stokes problem, when we do that, what happens? Well, very simple. Very simple. Maybe today I promised that I would do that in detail. I will obtain the adjoint of that operator, and we will see that it is this one. Okay. Let's check that the adjoint of the Stokes operator is this one. Okay, let's check that. Assuming, except for boundary values, okay, assuming that the subscales vanish on the element boundary. So except for boundary values, let us check that adjoint. So what is the Stokes operator? So we have the Stokes operator L of UP. So again, you will see that it is very important to write the problem as a single equation once more. Multiplied by the test function, BQ, is equal to minus nu Laplacian of U plus gradient of P, comma, nu Laplacian of B plus divergence of U, comma, Q. I put parentheses if you want. I put angle parentheses to to understand that this might not be defined globally, but anyway, whatever you want, either parentheses or that, just to explain the idea. So that is what it is, okay? And that's the original problem. And we have to find the operator L star such that this is equal to U P L star VQ. Okay? So we have to obtain L star by isolating U and P. That's the adjoint. Let's do it. Equal. First, we have minus nu Laplacian of U times V. Let me work a little bit on that. Well, anyway, I do it directly because it's ridiculous. So, when I have minus nu Laplacian of U, V, if I integrate by parts twice, it is easy to see that I will get U minus nu Laplacian of V. Okay? Because when I integrate twice by parts, I keep the sign and the derivatives will go from U to V. Okay, so this is this term. So for this term, we know that this is minus P divergence of B. Okay, so this is minus P divergence of B. And when I integrate that by parts, I get minus U gradient of Q. And plus boundary terms. Okay? Do you all follow this? If anybody doesn't follow, please let me know. Okay? So now I have that this is equal to U P multiplied by what? Multiplied by, look, U multiplied by minus nu Laplacian of U, excuse me, Laplacian of V. But U is also multiplying minus the gradient of the pressure test function, sorry. And P is multiplying minus the divergence of B. Okay? Minus the divergence of B. Have you seen that? So, therefore, we see that certainly the adjoint of the Stokes operator, you have to consider the equation as a single one. If you don't do that, you will not see why. If you consider the equation as a single one, we see that the adjoint of the Stokes operator is this one. So the first component is minus nu Laplacian of B minus gradient of Q, and the second component is minus the divergence of the velocity. You see? Okay, pues now that we know which is the Stokes, the adjoint of the Stokes, we just have to go ahead and see which is this term. Minus the adjoint will be plus here, and plus here, minus the adjoint. So plus everywhere. And then we have to multiply minus the adjoint times tau multiplied by the residual. And what we will get is this. So we have tau, the adjoint, with a change of sign, first component multiplied by the first component of the residual, plus tau 2, second component of the adjoint with the change of sign multiplied by the second component of the residual. And we see that that method is exactly the same as GLS except for the sign of the viscous term. Okay? And it is more convenient to have this sign for different reasons. And that's it. That's the end of the story. So we know how to stabilize that. What would happen if we have edges? We have to add that jump that we have seen before. If we have discontinuous pressure, if we have discontinuous pressure, we have to add that jump. So we know already all what I wanted to explain about the Stokes problem. So today we have finished a little bit earlier than, I think it doesn't make sense to start with Navier-Stokes. I think I will start directly tomorrow with Navier-Stokes. And that is it. Tomorrow we will see the important thing, Navier-Stokes. Okay, that's just a preliminary. Okay, so see you tomorrow then.